All right, so today I want to talk about the PV command or the pipe viewer command. It's super cool. We've used it before on this channel. I think it is amazing. At its core, it is a simple Unix utility you can pipe programs into or you can redirect output from. It reads from standard in, it writes to standard out, just like cat, just like, DD or whatever. But you can get statistics from it. You can get progress bars. You can get all sorts of things. It is a super cool thing to throw into your shell pipelines and kind of get some insight into what's going on. I'm not going to waste time describing it. Let's just jump right in. All right, so PV is a really cool command and it has a ton of usages, okay? Let's imagine I want to cat a really big file. I have user share dict words on my system. I run this. There is a giant word list here. There's a ton of different words. If I pipe this to word count minus L, we can see there are 235,000 words, okay? That's a ton. I can pipe this to PV. And now we get a progress bar on how long it took to actually write that to the screen. This is a really stupid example because it wrote it almost instantaneously. Look, it took 0 seconds, it read it this fast, and this is how much data it had to read. So at 38 megs a second, it read 2 megs pretty fast, in less than a second. Well, okay, what do? We use cat. What if we were to use slow cat? Slow cat is a program, as you can guess. It's like cat, but it's slow. So let's do this and see what happens. Okay, we're putting out the information and we have a nice little progress bar there. That's pretty cool, but the progress bar is kind of a mess. So typically what you would do is you would redirect this, say we would redirect this to like a file, we could redirect this to a network source, we could redirect this to dev null. So look at this. Now we can get an idea of how fast slow cat is running. Obviously, this could be any command. This could be any command you're running that outputs data to standard out that you want to do in your pipeline or whatever, and you just want a progress bar. This is a super fast way to get a nice progress bar here. Look, you can see it's read in 699 bytes. It's taken 20 seconds so far. It's reading at around 42 bytes a second. And this progress bar, it doesn't know the size of the file because think about it. Slowcat is the one reading this file. PV doesn't know the size of that file, so it can't actually estimate how long it's going to take. We can give it to it as an argument. PV would normally try and detect it if it was given the name of the file as an argument, but then PV would just read from that file directly. So we can we can help it out a little bit. So if we do an /-l on user share dict words, we can see that it's a symlink. I always forget this, to web 2. Let's go ahead and look at web 2. We can see that here. Here is the size of the file in bytes. That's how big this file is. So we can help out PV. If we know this information, we can do a -- size and give it here. And this tells PV basically when calculating the progress, here's the denominator, okay? We've read 100 or 200 bytes out of this many bytes. And you can see my ETA is this will take 17 hours to run at the current speed. We're not gonna sit here for that long. Oh, 16 hours. Look, it's even going a little bit faster. So now it knows a percentage, it knows an ETA. This is super cool. This is super awesome. When you're piping into PV, it can't know the name of the size unless you give it some sort of hint. This is your hint into PV. Here's something cool. You're probably wondering, Dave, what is slow cat? I don't have that on my system. Is that just a version of cat that's slow? Check this out. You ready for this? Look at this. Slow cat's an alias on my system. What's it an alias to? PV. It's an alias to PV. So slowcat ran this. Let's go ahead and run that ourselves because this is exactly what's being run, right? We run this and we get this. So how is it accomplishing it? There's got to be something going on here. We're passing it a -L, we're passing it a -cap L5 and a -Q. Let's go figure out what those are. First thing we were passing was a -L. I think we can pipe this to highlight for -L. And there you go, you can see it's highlighted right here. Line mode, count lines instead of bytes. So we put this in line mode, so PV is expecting lines instead of bytes. This is relevant for the next flag that we use, which was -cap L. Go ahead and search for this, we'll highlight it. And look, right here, rate limit. Limit transfer to rate bytes per second. So, as you can see right here, we were running -L5. This tells it process 5 bytes a second. Now here's the thing, we put in line mode, so now it doesn't mean bytes, it means 5 lines a second. Look at this. This is outputting a line. This is outputting 5 lines in a second or a line every 0.2 seconds. That's what's happening here. If we were to get rid of that first -L, we're going to put it into byte mode instead of line mode. And now it's processing 5 bytes a second. So as you can see, it's 1 character every 0.2 seconds. So a little bit different. PV is super nice just for having a line mode, a line aware mode. It makes it super useful for these kind of situations where you're not dealing with binary data, you're dealing with text data. So by default, PV kind of works with raw binary data. You can give it a -L to work in line mode. There is also a -Q there. You could probably guess what it is just based on the name. I don't know why I pulled the man page. There's also a really nice man page. Man page is super nice. But let's do a PV -H HL for -Q, I believe it was. And -Q is quiet. Do not output any transfer information at all. So PV is super good because it can be a rate limiter without actually outputting a progress bar. So even though it's called pipe viewer, it can actually modify some of the behavior of it, or at least slow it down. So you could like PV a file with a rate limit of like 100 bytes, and then you could pipe that to SSH and write that out to a file on a remote end. I just came up with that example. Why don't I just show that example? Because that example seems super cool. Actually, we have a file right here, don't we? We have user shared dict words. Let's change this to do, I don't know, 5,000 lines a second. No, it's still not going to finish any sort of timely manner. Let's change this to be 10,000 lines, 50,000 lines a second. There we go. That's significantly faster, but not fast enough where if you blink, you miss it. So now we have this PV command. We could pipe that to SSH void, which is the name of a system I have. You would just put your system name here, and then we could write it to cat read in from standard in, redirect to words.txt. And if you run this, it will work, but we have the -q flag because it's quiet. Let's go ahead and get rid of that -q flag and look at what happens here. We have a progress bar. We have a progress bar. Obviously, you could just SCP the file over, but this is super useful if you're in some sort of pipeline. If I were running like tar-cf to create a tar file, instead of saying file.tar, I could say a hyphen here. I could say, let's tar up my bin directory. I could pipe that to PV, and then I could pipe that to SSH void, and then cat that into bin.tar. You could do something like that if you wanted that kind of a progress bar. So it doesn't exist as a file. It gets turned into a file in the remote end, but PV will still give you that progress bar. But yeah, look how nice this is. That is super nice, and it just works. We can verify this. I'll verify this once it's done. We can just SSH into void, and we can do a word count -l on words.txt, and we can see that we have the whole file there. It's on this remote machine. So that's super cool. That's awesome. Also, if you noticed, I kind of glossed over some things. I'll help you out real quick. There's a ton of stuff here, guys. I can't go over all this in a video. I would say spend some time looking through this. There's a ton of things Pipe Viewer can do. It is super cool software. Shout out Pipe Viewer, dude. It's just awesome. Also, people are going to ask, I always get comments on this, HL to highlight text is actually just rip grep with the -- pass-through flag. So that's all that's going on there. That's how I highlight text. It's like grep, but it doesn't actually do any filtering. Also, while we're here, I kind of just mentioned it in passing, but I think it would make a good example. Let's say we're going to tar something, okay? We'll do tar cf to create a tar. We'll call it file.tar, and we'll tar up our /bin directory. Okay, we get a little warning, but it still worked. We can look at this file with ls-lh, and we can see that it's a 10 megabyte file. Okay, cool. That's awesome. We can also gzip this file. So this will get rid of the original file, and it will compress it. Now, if we do an ls-lh, I'm going to tab complete. Notice the original file's gone. We just have the tar.gz. 3.6 megs. So we compress it from 10 to 3.6. That's super cool. Here's the thing. We could do that all in a pipeline. Instead of having to create the intermediate file on our file system, we can do it all at once. We can say cf hyphen for the name of the file, which will be standard out, and we can tar up /bin. This will just emit them to the screen. This will just emit bytes to the screen. I probably don't want this. I can show it to you guys. If I pipe it to a hex dump, you can see that like, wow, that looks really cool. I look like a hacker on like some Hollywood movie. It's not actually useful. First of all, we can pipe it to gzip, and now we have the compressed data going to the screen. So very much the same thing. It's going to be just a lot of this, but with a lot less zeros. It's going to look more like random data kind of. Now we have the gzip version. We could write this out to file.tar.gz, look at the file, and we can see that it's 3.6 megs again. It's basically going to be the same file. So why did I do that? Because we have a pipeline. Look at this. We have a pipeline. We could just pipe PV here. You could pipe cat here if you wanted. It would do nothing. Cat reads in from standard in, writes standard out. It's totally fine to throw it here. Instead, let's just throw PV here and let's see what happens. Look at that. We got a progress bar. Now, this ran way too fast. Look, we processed 31 megs a second. The input file is only 10 megs, so that's not super useful again. But if we were to give it, let's give it a bigger directory. I'm trying to think of a big directory. I'm on my Mac, so I can just give it the movies directory. We can just give it the OBS movie. So I'm actually writing to that directory right now. Maybe that'll be a bit much. Let's just write the projects directory. There's a lot of files in here. In fact, I'm not even going to write to the file system. Let's just go ahead and pipe this to dev null. So let's take a look at what we're doing here. We are tarring this directory to standard out, piping it to PV, piping it to gzip, and then writing it to dev null. And look at this. You can see here's the amount of data we've processed. Here's how long it's been. Here's how fast it's currently processing data. Remember, it's sitting here. So here's how fast data is being written out of tar and piped into gzip. And you can see that we don't know how much data is here. It's still tarring the file. Like we have no idea. So we're not going to get a meaningful progress bar. We're just going to get some sort of animated thing here, which is fine. We don't know the size of it. That makes perfect sense. So this is super cool. This is awesome to see this. Likewise, an alternative way of doing this, I've seen people do this in the past. I think someone even commented on one of my videos that they had done something like this. I had written out a file. So let's say I wanted to make a file of just zeros, just all zeros in the file. Well, that's super easy. I can dd, the input file would be dev 0, and if I run this right now, we're just gonna spew a whole bunch of zeros to the screen. Not the ASCII character 0, but like literal null bytes. So if I pipe this, you can see they're all null bytes, and it will just go forever. It's a pseudo device that your kernel gives you, and it's beautiful, it's awesome. We can also specify an output file. I'm just gonna say dev null, so we're not doing anything. We're reading in a file and we're writing it out to dev null. That's super great. With DD, I know newer versions of DD, I think all of the versions I've encountered now have this. This wasn't always the case in the past, but you now have a status equals progress, I believe. And you can get this progress bar so you can see like how fast it's going, how much it's transferred and stuff. But you might be in a situation where your output and your input's a little bit different. Maybe one's coming from a network source, maybe you're writing to a network source. Who knows? You could simulate this with PV. So reading in from dev 0, we could pipe it to PV, we could pipe it to DD again to output to dev null. So this is exactly the same, but DD is not giving us the status, pipe viewer is giving us the status. So super cool, you can toss that in there because then you could do all sorts of stuff. Like I could pipe this to like netcat and I could just write it to like a server if I had something else like listening on port like 5600 or something. I don't know, I'm just making up stuff, but like you could totally do something like that. It's super cool, it's super useful. Real quick, while researching for this video, I found this really cool flag to PV I did not know existed. PV-T. Look at this. It's just a timer. It's just a timer. You can just run PV-T and it's just a timer. So as long as something's running, as long as the input is open, if I control D, then I can close the standard in, which causes PV to be done. It will just emit a timer to the screen. This is super useful because if you're running a command, some really long command, and you pipe that to PV-T, well that, I thought I made an alias for that. That would have been really cool for the video. Just pretend that's an alias. Well, actually, I have movie magic. So if we're going to take some really long command and pipe that to PV-T, look at this. We have a timer. We can see how long this command is taking to run. As long as it exists somewhere in the pipeline, we will get this nice little clock here. And PV, of course, reads in from standard in and writes the standard out. So you can just toss this in your pipeline and still redirect right through it. It just silently transfers data between the two. Super nice. And so this was always defined the whole time. I didn't just define this for this part of the video and cut it. You can see that some really long command just sleeps for 10 seconds. So if you have a command that does something that takes a while, in this example, we're just fabricating it, you can see that sleeping for 10 seconds took 9 seconds. So yeah, beautiful. That's awesome. So for this example, I'm going to go back to the tar command that we had, tar -cf, write the standard out, and let's tar up my movie projects just because I know it's a big directory and there's a lot to tar up there. We can pipe this to PV, then we can pipe this to gzip, then we can pipe it to PV again, and we can write it to the output file. In this example, I'm using dev null. I don't want to save any of this data, but we can have 2 PVs running, okay? And if we run this, you only see one thing of output here, right? They're both kind of trying to output there, and things can get a little bit messed up. Luckily, PV accounts for this, and you can do something to help it. So the flag that it needs is -C. This is short for -- cursor. And this will allow multiple PVs to work in the same pipeline. They will detect they're on the same terminal, and they will format themselves nicely, and they will both take up one line. So you can see that, okay, one of them's operating at this speed and the other one's operating at this speed. So they have different byte counts now. Now, as you can see, the byte count's a little bit different. Look, the one at the top is a little bit bigger. So I'm willing to bet the one's a little bit bigger is here, and the one's a little bit smaller is here, because this one's after compression and this one's before compression. But that's just a gamble. That's a bet. Because the way pipelines are executed in Bash and other shells, at least the ones that I'm aware of, there's no guarantee of the order that these are executed in. All these commands will be executed pretty much at the same time. You can think of it as the same time, and they all get wired together like this. So it's not like tar runs and then PV runs and then gzip runs and then PV runs. This messes up a lot of people when they deal with terminals. When they first learn the terminal or the shell, these all start running at the same time because this PV needs to be running, reading from gzip, which needs to be running, reading from PV, which needs to be running, reading from tar. They all have to to be able to write to some sort of valid target. So the processes have to be in place before they even start talking. They're not aware of which one's running first and which one's running second. They just take the first slot that's available. I think we got lucky here and we won the race and it worked out like this, but it may not in the future. So what you can do to account for this is there is another flag, --name or -capn. If you do -capn, you could say tar here, and we can go over here and we can say -capn gzip. So we give them both names. Of course, you can condense these flags if you want to -c capn. I do this a lot. When you run this, take a look at this. We have the tar and we have the gzip, and now you can clearly see which one is running. So it makes sense. We got the same order again. The smaller value is the gzip, which makes perfect sense because we're compressing it. We should be able to shrink down some of these bytes, you know? So this is super cool. You can give it the -c and the -N flag. Now I'm thinking about it, you can totally just like contrive a scenario too. Let me think, you don't actually have to give it any input. We could just run PV on its own. If we just run this, it should just run. Like it doesn't have to do anything. No data is being transferred between the two. I kind of like seeing the data transfer. Let's just pipe yes into PV. So, you know, yes just outputs Y to the screen like that. We could pipe yes into PV, and we can say line mode -cap_l will allow 5 lines at a time. So this is what we get. There's also a progress bar there. So let's give it a -c, so we're in cursor mode, and a -capn, so we can give it a name, and we will call this 1. The name of it is 1. So we get that, and you can see, well, it's a little bit tough with the actual command outputting data. But let's do this first. Pipe it to PV-CN2. Pipe it to PV-CN3. Pipe it to PV-CN4. Write this out to dev null. Now hold on, because I realized I wrote CV and not PV. There we go. If we run this, now we should have 4 different progress bar. 1, 3, 2, 4. As you can see, the order is not guaranteed. It's not consistent. But you can see this is a super cool way of seeing like all the progress bars at once. Oh, interesting that this one doesn't have B's because it's in line mode. Oh, that's cute. It's showing you how many lines were read. That's awesome. I like that. I like that so much I'm going to disable line mode. But yeah, so let's change that to, I don't know, 10 bytes at a time is good enough. And now, okay, now they're all aligned. You can see they're all reading bytes like this. Oh, that's super cool to see. That's really, really neat to see. So 1, 3, 4, 2. We got a completely different ordering this time. Like I said, the order is not consistent, but they at least can write to different parts of the screen. 2, 1, 3, 4. You can't rely on the orders. Always give it the name flag if you're giving it the -c. There might be a hack. There might be a hacky way to do this, okay? We're in Bash. We can put these in subshells. You just wrap parentheses around these, and these execute in a subshell. And this won't do anything on its own. Was it 4? There we go. So if we run this, 1, 3, 2, 4, we almost got lucky. But because they're in subshells, we might be able to do something fun here. We might be able to sleep for 1 second and then run PV. This can sleep for 2 seconds. Because they're in subshell, they should already start reading the data. It's just sleep won't do anything with it, and this should sleep for 3 seconds. This is super hacky. I don't know if I recommend you guys do this. I don't even know if it's going to work. Let's find out. Okay, that's pretty cool. We had to artificially put a delay in there. I can't say that this is like the cleanest way to do it, but like you guarantee the order. Well, you don't guarantee the ordering. You set yourself up to win the race condition by artificially putting sleeps in there. PSA to anyone watching, if you're dealing with a race condition, don't fix it with sleeps, okay? You're not actually fixing the underlying condition. But for this example, this is pretty sick. This is pretty cool. You gotta admit, this is a pretty cool hack, okay? And now I want to show you guys something really cool, because I actually didn't know how this was being accomplished. Because when I look at this, I'm looking at this, right? I'm like, okay, this one's running, this one's running, this one's running, and this one's running, and they know that there's 4 running, so they know how to order themselves. They don't know the right order to put themselves in. That makes sense. But they do know that there's supposedly 4 running, so it knows where to jump the cursor to redraw the progress bar. And in my brain, I'm like, how? How are they communicating with each other? Like, if you know how pipelines work, they only transfer data between standard in and standard out, and that's the raw bytes. We're not modifying that data. So like, How are they talking to each other? How are they aware that they're for them? Are they using temporary files with like some known location? Have they all synchronized on that? Like, what were they doing? So I'm going to show you guys. We're going to dig into the pipe viewer source code because that's the kind of stuff we do on this channel. If you guys like that content, you like getting in the nerdy nitty gritty here, hit that subscribe button. Okay, I have 113,000 subscribers at the time of this recording. Let's get that way up. Okay, I want to get that I want to get that million subscriber play button. That's my new goal. I don't think that will ever happen. I got the 100,000 subscriber plaque. I don't know if I'm getting the gold one. Yo, check it out. Check it out. But yeah, let's do it. Let's dive into some code. Cool. So I got the website pulled up here. I will go ahead and I will put this in the description for anyone who wants to check it out. Let's take a look what we got here. We got the source code right here. So right click, copy link. Let's hop on over to the terminal. Let's just go to temp directory. And let's make dir pv. There we go. So now I can curl -o this. There we go. And now we can tar xf pv. And now we have this pv directory with 1.111.0. Cool. How do we compile it? There's a readme.markdown. That's super nice. Look at this. The typical process for a system-wide install is configure, make, sudo make install. So it looks like there's configure and there's make. That seems simple enough. So let's just run configure, assume this works, and we'll just run make. Cool, so that didn't take too long. Now we can run make. Technically, guys, we could run make and we could pipe it to PV -T and it will print out a little timer. It'll be interspersed with the output, so it'll be super ugly, but you could totally do this. And, oh wow, we can see, look at that, 2 seconds, beautiful. Okay. So now we have, do a nice little ls here. Look at that. We have a PV command. So we have a freshly compiled PV command on this version on my system. That's awesome. I don't even know why I bothered compiling it. I was just going to go to the source code. My brain just went to autopilot there. So I was browsing the source code on, I think it was Codeberg is where it's stored. And I found this file and I'll show you guys. In source, there's PV, there's cursor.c. So I found it on the website, but I'm going to go ahead and pull it up here. I was blown away at how they were accomplishing the PV commands actually talking to each other. It's really, really cool. Cursor positioning functions. All of it happens in cursor.c. If IPC is available, then a shared memory segment is used to coordinate cursor positioning across multiple instances of PV. The shared memory segment contains an integer, which is the original Y coordinate of the first PV process. So it knows where to start, and then it knows the offset from there. Super cool. However, some OSs, FreeBSD and macOS so far, don't allow locking of a terminal. So if a terminal locking doesn't work, a separate lock file is used and cursor positioning is abandoned if that also fails. So that is super cool to see. I don't actually know if the locking mechanism is working on macOS or not. I'm running on macOS. I don't know when this comment was written, but that is super cool. So we just do a nice little search for SHM. Shared memory typically shows up like this, SHM functions. Get the current number of processes attached to our shared memory segment. Find out how many PV processes in total are running in cursor mode, including this process, and store it in this. So we can keep track of the number running and the original Y coordinate. And then when you know which number you are, you can just draw your cursor down there, draw your status bar, and then let the other processes take over and draw them. Really clever, really, really clever solution. Now I'm curious though, because I talked about locking the terminal. To avoid a race condition, the function locks the terminal with PV-CRS lock while attaching and checking. The race condition is that another process could attach before this one checks, such that no process ends up getting the attached count of 1. Okay, yep, makes sense. So we lock the terminal and we use this function that is defined here. Lock the terminal in a given file descriptor. Falling back to using a lock file, the terminal itself cannot be locked. Interesting. Okay, so this actually will handle the lock file logic too. Oh yeah, so if there was a failure and it was not interrupted, then we do open lock file. Otherwise you print an error here. That's super cool. What is this debug function? Can I make this debug output show to the screen? Because that would be really cool. Is there a verbose or a debug or something to get this stuff to show to the screen? Or do I have to compile it with debug support? I'm curious how this works. You know, let's look at the options file. If def enable debugging, then it gives you a debug flag, a dash debug. Unrecognized option. Okay, so maybe in the configure script there would be something about debugging here. Enable debugging, compile with debugging support. Okay, that's cool. enable debugging. Let's reconfigure it. Then we will recompile it. And then we will get that debug flag, which will give us that debug output. And then we can see if we're able to actually lock the terminal or not on my Mac OS installation right here. Can I just rerun make? Okay, it does know that the files need to be remade. Okay, cool. Sometimes you have to make clean before that, but this seems like it works. So if I have this now, look at this. We now have a dash exclamation mark or a dash dash debug, write debug logs to file. Okay, pv dash c dash n foo dash dash debug, I don't know, debug.log. There we go. We'll run this, let it run for a little bit. Control C, cat debug.log. Oh, wow, there's a lot in there. Okay, cool. Yeah, what do we have here? Okay, let's cut this. Delimiter of space, we want field, let's say, I don't know, 7 and over. Maybe that's a little bit too far. There we go, that looks better. Maybe 5 and over? No, let's do 6 and over. I guess we could look for cursor. Yeah, let's do 5 and over. Grep for cursor.c. There we go. Terminal lock acquired. Okay, well, in this year, in our current year, we are able to lock the terminal on macOS. That is pretty neat. We can see that there's one PV. Okay, Y position is 31. We are the first to attach. Terminal lock released. Okay, so you get the lock, you attach, you figure that out, you set up the shared memory page, and then you release the lock. That makes perfect sense. Terminal lock acquired, terminal lock release, acquired release. Okay, that's clever then. So every time you want to write an update, you lock the terminal, you write your update, which involves moving the cursor and writing your progress bar. That's super cool because you can't guarantee the writes are going to be atomic when you're writing both the, ANSI escape sequence to move the cursor and then all the text that goes with it. You can't really guarantee that, but if you lock the terminal, you can really guarantee that. So that's super cool. That's very clever. I hope you guys enjoy this little debug into the PV source code. This is super cool. It's a great tool. I've been using it for years, probably decades at this point. In fact, yeah, now I think about it, it's got a little donate link and a buy me a coffee. I will take care of that after this video. Yeah, so that's super cool. Hope you guys enjoyed this deep dive into Pipe Viewer. It's a super cool tool. I love it. Super useful. And of course, I can't end a video without giving a shout out to my patrons over at Patreon. Thank you so much for your continued support. If you want to get your name at the end of one of my videos, sign up for my Patreon. It'll be linked in the description. Check this out. You guys ready? Look at how people hack the names. Patreon doesn't do any filtering of the names. Well, that's not true. They do some filtering, but Patreon lets you put in an ANSI escape character. The ANSI escape character, which can make ANSI escape sequences in your name. And my script doesn't do any sort of sanitization. And as long as you guys are cool and you don't do anything super weird, I'm leaving it in the video because I think it's super awesome. As long as everyone's being represented, you're paying me your name should be up here. So super cool. I love that you guys mess with the script. I think it's super fun. Check it out. We have 123 active members. That's super awesome. Look at that. It's our subscriber count. And look at that. It's even the timestamp. Look at all the metadata I put in my videos. How cool. And yeah, that's all I got for you. Take care, everyone. See ya.